Hi, I'm Scott Vaughn, and this is a presentation that my good friend and colleague Hector Maracuto and I worked on together, and that I presented at the Mathematical Association of America MathFest conference in Philadelphia earlier this month in August 2022. So the topics that I'll present are the mathematical modeling of gliding motion of an airplane. We'll look at deriving the equations of gliding motion. We'll solve those equations numerically, that is to say, using the computer. We'll collect data using flight simulators and fit that data to curves using the mathematical model, and we'll look at student projects and exercises that come from this material. So when I talk about gliding motion, I'm going to be talking about a specific phenomena that can occur in gliding motion, which is this longitudinal oscillation, or phugoid motion. And this term phugoid is from a Greek word for flight. It was coined by Frederick Lanchester, who lived from 1868 to 1946. He was an English polymath and engineer, and the mathematical model that we're developing was originally derived by Nikolai Zhukovsky, who lived from 1847 to 1921. He was a Russian scientist, mathematician, and engineer. And to start off, I'll mention a few articles that point to the fascinating theoretical and real-life applications of this work. So first, an article titled A Study of the Phugoid Motion of an Airplane at Supersonic and Hypersonic Speeds by Uso Walter in 1967 at Caltech. It's an analysis of the flight dynamics of the X-15 rocket-powered aircraft that was operated by the Air Force and NASA. And this topic and paper, something I hope to come back to in another video later. It's something I'm really fascinated by. I'm remembering this dramatic opening scene in the movie First Man of Neil Armstrong piloting an X-15 and traveling so fast that he bounces off the outer edge of the Earth's atmosphere. The next paper here is titled Phugoid Motion Simulation of a Supersonic Transport Using Navier-Stokes Equations by Guru Guruswamy at NASA's Ames Research Center. This is a much more recent paper, and I'll just mention the Clay Mathematics Institute has said a fundamental understanding of the Navier-Stokes equations is one of the 7 most important open problems in all of mathematics, and they're offering a $1 million prize for a complete solution. And then finally, this article, Engineers Design Motorless Sailplane for Mars Exploration, from 2022 by Emily Diekman from the College of Engineering at the University of Arizona. It's a fascinating article. I mean, NASA has already sent a helicopter to Mars. Imagine an energy-efficient sailplane gliding for hours, released into the atmosphere by a balloon. Okay, so now let's go through deriving the equations that will model this phugoid motion. So the question that's really driving all of this are, what are the speed and pitch of the glider over time? So here's a picture of a glider in a 2-dimensional coordinate system with an x and y axis, and I've got the pitch of the glider as this angle theta. It's the direction of travel. So I'm going to take pitch and direction of travel to be the same here in a very simplified model. And I've got this vector t that is the tangent vector, that is the tangent to the velocity. It's the direction the glider is traveling. And I've got a perpendicular vector, the n, which is a unit normal vector that is perpendicular to the direction of travel and perpendicular to the unit tangent vector. And I'm going to analyze the lift and the drag and the weight of the glider over time. So expressing the lift vector, this is a force that is in the direction of the unit normal vector, and it's made up of these components that are the air density, the coefficient of lift, and the surface area of the glider. Now these 3 values I'll take to be constants in this derivation: constant air density, constant coefficient of lift, and constant surface area. Now the surface area should stay constant, but coefficient of lift doesn't really stay constant. It changes with pitch. But I'm going to assume it's constant here for a simplified derivation, a simplified model. The drag force is opposite to the direction that we're traveling, and that's why there's a negative here. It's also made up of air density, a factor for air density, a factor for the coefficient of drag. Again, something that's developed experimentally and actually does change, but it's taken to be a constant here, and times the surface area times the velocity squared. Now, technically, this is the speed. Both of these values for v are actually the speed, actually values that we'll ultimately be solving for. But sometimes it's just convenient to say velocity when you write the letter v for speed. So to distinguish, there's the velocity, which is both the speed and direction. It's composed of the speed, which is this v, and the unit tangent. The unit tangent encapsulates the direction in which you're traveling. The v is just the speed at which you're moving, and together that makes a velocity vector. That velocity vector would be exactly parallel to the unit tangent vector, so pointing in the same direction as that vector t. And of course, we've got the weight vector, which is made up of the mass of the glider, which I'll assume to be constant, and the acceleration due to gravity, which again, constant. And this is directly downward in our coordinate system, and so therefore parallel to the unit vector j. Now what I want to do is add together the lift, drag, and weight and add them up and equate that to the mass times acceleration. In order to add them all together, what I need to do is express them all in terms of some kind of common unit or common vector or common unit. So that'll be the unit normal and unit tangent vectors. So what I'll do is I'll take the weight vector and break it up into its normal component and tangential components, as you see here. This is a exercise in trigonometry and also just vector projections. So the sum of all the forces here is the mass times acceleration, and that's where we can begin to actually develop two equations that we can solve. So adding together the sum of all the forces here, just the lift, drag, and weight. Of course, notice that there's no thrust. This is a glider. It doesn't have any thrust in this model. So we have the lift and the drag and the weight all added together. But that means we have components of the sum of all the forces that are normal to the motion and tangential to the motion. And so we can collect together the normal components of the sum of all the forces, and we can add together the tangential components of the sum of all the forces and equate that to the mass times acceleration. But of course, the acceleration is the change in velocity over time, the derivative of the velocity over time. So again, what I'm solving for is actually the speed, which is this v, it's a function of time, and theta, which is the pitch, and it's a function of time. So the velocity, because it is parallel to the unit tangent vector, I can express it as v times the unit tangent vector. And that velocity, or actually the acceleration, because it's the derivative of the velocity, I'm going to take a derivative of this expression, v times unit tangent vector. And that's the product rule. So the derivative of this v with respect to t first times the unit tangent plus the first times the derivative of the second component here, the derivative of the unit tangent vector. The unit tangent vector depends on theta, which depends on time. And so when I take a derivative of the unit tangent vector with respect to t, time, I get this extra factor from the chain rule, the derivative of theta with respect to t. So that's what I'm doing here is the derivative of cosine is negative sine times the derivative of theta with respect to t. And the derivative of sine, that's cosine times the derivative of theta with respect to t because of the chain rule, because the fact that the unit tangent depends on theta, which depends on time. And I could factor out that d theta dt out of each of these components of this vector here and write it in front and recognize that that's the unit normal vector. And bingo, there I have the acceleration written in terms of its tangential component and normal components. So I know that the sum of all the forces is the mass times acceleration, but that acceleration is change in velocity over time. And that change in velocity over time can be broken up into tangential and normal components. So I just derived that the mass times acceleration can be written in terms of these tangential and normal components of acceleration. And I've also just derived that the sum of all the three forces, lift, drag, and weight, can be written in terms of their normal and tangential components. And therefore, what I could do is equate from the left-hand side, the tangential component on the left-hand side of this equation with the tangential component on the right-hand side, and equate the normal component on the left-hand side with the normal component on the right-hand side. And that's where we get these two equations. These are two differential equations because they involve the derivative of the velocity over time, or really the rate, the linear speed, and the change in the angle over time. So those are my derivatives, and that's why this is a differential equation. And they're nonlinear differential equations because the variable that we're solving for here, v, technically the speed, it's squared. So it's a nonlinear system of differential equations. There's a lot of variables there, but I'm going to just point out again that the m is a constant, the air density, the coefficient of drag, and the surface area, these are all constant. This m times g, again, constant. Really, the variables here are time, the speed v, and the angle theta that we're solving for. So there is my system of nonlinear differential equations. I'm solving for v of t, the speed over time, and theta of t, the pitch over time. And I'm assuming that the m value, the mass and the air density, rho, the coefficient of lift, the coefficient of drag, surface area, and gravity, all of these values are constant. To rewrite this in a way that it's convenient to solve on the computer, I'm going to divide both equations by m. So if I divide here on both sides by this m, that m will just become a denominator here with the 2. And when I divide this term here, the m's cancel out, and I just get a g times sine theta. And when I take the second equation and divide both sides by m, once again, that m just kind of gets tucked in there as a constant. I divide this term by m, and the m disappears, and I just get g times cosine theta. And so now what I'll do is I'll just make this assumption that the coefficient of drag, air density, surface area, and mass of the glider are all constant during the flight. It's not really true, but it's a useful simplification that leads to a relatively simple system of equations that are easy to put in the computer and find a solution. So I'm taking this group of constants, air density, coefficient of lift, surface area, mass of the glider, and all of that I'm renaming a lift constant. So this mu L, this is not the coefficient of lift anymore. It's a combination of several constants that I'll just now call lift constant. And this constant I'll just call the drag constant. So that's what it looks like when it goes into the computer, those two differential equations that we've derived with fairly simple assumptions, right? And it's still actually really hard to solve this system of differential equations. We'll use the computer to do it. When we do that, we'll also need to have initial conditions. What was the initial speed and the initial angle? And the drag constant, lift constant, and gravity will all be taken to be constant. So now that we have the equations derived, what we could do now is look at 3 different flight simulators that model the flight of a glider and compare the results in these games with the mathematical model that we just derived. We'll look at Geo-FS, which is a free flight simulator that runs in a web browser. You can use lots of different airplanes and locations in that program. We'll look at Kerbal Space Program. It's available for PC and Mac and PlayStation and Xbox. You could download for the PC and the Mac from kerbalspaceprogram.com or steam.com, and you can choose pre-made, ready to fly, or you can build your own airplanes and rockets and other craft, and you can test this out with multiple planets with different atmospheres. And we'll also look at Microsoft Flight Simulator 2020 that's available for PC and Xbox. And it has realistic flight dynamics and controls and a very realistic world map. And it has free downloadable gliders that you can include and experiment with. So when we're modeling the flight of a glider, we'll need to set the initial altitude, speed, and pitch, and then collect flight data, measure the altitude and the speed and the pitch over time, and we'll look for appropriate lift and drag constants to fit a curve that is from the numerical solution from the computer to this collected data, and we are modeling this longitudinal or phugoid oscillation of the glider. So let's go through now and look at these different flight simulators and compare with the solutions in the mathematical model. And I will go through a video clip of each of these flight simulators at the end of this presentation. So first example here from Geo-FS, the aircraft here is the Alice Sports Silent 2 Electro. Initial altitude 8460 feet, initial speed 60 knots, initial pitch 0 degrees, and you can see a dial here for altitude, pitch, and speed. And the way that I collect data is just hit escape or pause in the game and write those down. I'm writing down the pitch, I'm writing down the altitude and the speed at like 5-second intervals. So, and this is the code in Mathematica that will solve that set of differential equations. So you see over here initial altitude in this particular example, 8460 feet, but I'll convert that into meters, and I'll take the initial 60 knots, convert that to meters per second. Here's my theta 0, that's 0, that's the initial pitch. And I have a lift constant and a drag constant that will fit the data that I've already collected. And there's the acceleration due to gravity. So you can see that I'm using the ND-solve, numerical differential equation solver in Mathematica, and you can just make out here the derivative with respect to v, dv dt, is negative g sine theta, that's here, minus md, that's the mu drag v squared. That's the equation there with a negative, and then comma, there's my other equation. Here I have my initial conditions and the two functions that I'm solving for and the time interval, and I take the solutions to the numerical differential equation solver from Mathematica and define them as these functions speed and angle. So once I have these functions speed and angle of a glider over time, I can integrate those to find x and y over time, the position. So I have x and y positions of the glider over time, and then I can plot that position with this parametric plot function. And so we can see that longitudinal oscillation up and down. So maybe just pause, like why is it going up and down like this? So as the glider begins its motion, it might start to fall because it doesn't have any thrust, but as it falls, it will pick up speed. As it picks up speed, that can generate lift, and as it generates lift, that can actually bring it up again. And so it could oscillate up and down. As it comes back up, though, it may slow down and therefore lose lift and then fall back down. So it'll just oscillate up and down like that under the right conditions. And so that's what we're seeing in this particular example. And this is actually just the black dots are the collected data from the game. I was just hitting pause, writing down the altitude about every 5 seconds over about a 1 minute period. And I looked at the solution from Mathematica for the height and plotted that. And of course, this is a really fantastic fit. This is a plot of the speed. The curve, the blue curve, is the solution from the differential equations, and those black dots are data that was collected in the game. So another pretty good fit, and pitch over time here as well. The black dots are the what I recorded as the pitch of the aircraft, and the curve is the solution to the differential equation. Another example here in Kerbal Space Program, this is the WG1. So I should say thank you to Christian Hakem, because I downloaded this from the website Kerbal X, where I found this aircraft. So in this example, we're looking at an initial altitude of 2483 meters, initial speed of 203 meters, and again, an initial pitch of 0 degrees. And solving the set of differential equations with this pair of lift and drag constants and plotting the position as I had done in the previous example. I've got a nice loop here in the flight, and that's the position, the solution for the position in the mathematical model, and we'll look at how that compares to actually what the glider did in the game. Here is recorded points that are the height in meters over time in seconds. The points are the data, and the curve is the solution from Mathematica. And Here's a plot of the speed in meters per second over the first minute, recording the speed about every 5 seconds and matching that with a solution that comes from the differential equations that was solved in Mathematica. And then one more example here with Microsoft Flight Simulator 2020. This is the DG-808, which starts at 8640 feet at 154 knots with an initial pitch of 0 degrees. And it also goes through some loop-to-loops, and I found lift and drag constants that I use in the modeling in the computer. It produces a curve for speed over time that closely matches the actual data that I collected. Actually, what's happening, of course, is I'm collecting the data and then finding drag and lift constants that closely match that data that I collected. So this is an exercise that can teach some mathematics, because you can really generate these virtual math labs. You could try different airplanes in different starting conditions. You could find lift and drag constants that match collected data from the game, and then you can optimize that curve's fit. You could plot the collected data and the mathematical model together. It's an exercise in doing a research paper and just the logistics of making that plot work in different software packages. In KSP, you could try different planets with different atmospheres and different constants for the acceleration due to gravity. And you could explore those conditions under which the glider will actually do a loop, and compute lift to drag ratio and glide ratio from the data and the model and compare them. As far as some exercises that would be useful in a math class, you could show that these two vectors, n and t, are always perpendicular. You could show that the vector j is equivalent to cos theta n times sine theta t. And you could go through this exercise of just writing the force of the weight, which is equal to negative mg times the unit j vector, in terms of the unit normal and unit tangent. And these examples are essentially what I worked through already in this video. Some other questions that go a little bit beyond what I've done right here, you could actually relate these equations to determine the terminal velocity and this idea of what's called trim velocity, which is a fascinating topic exploration right there. I have solutions to these exercises on this website, sites.google.com, view KSP Math. Okay, so that was the presentation, and I have this video clip of the examples that I'll share now. And just one more thought comes to mind before I run these clips. It's a fun thought for me because it sounds sort of philosophical. We've just developed a simulation of a simulation. We developed a simple mathematical model here just now of a much more complex mathematical model used in the computer game. Itself a complex mathematical model of a real phenomena in nature. This is an interesting thing to explore. How the computer models of natural phenomena, for example, laws of physics, are modeled in the computer and are sometimes closer to textbook models of physics than to real life, which makes using games as virtual labs an interesting way to teach math and physics. So here are the video clips. Here you can watch the altitude of the glider as it oscillates up and down, starting at around 8,460 feet and dropping to about 7,800 feet, but then returning to a second peak in altitude at around 8,260 feet. And watch as the speed oscillates between 60 and 130 knots, and the pitch oscillates between about minus 30 and 20 degrees. This is the game Kerbal Space Program, and we begin with the aircraft moving under thrust from the engine, but then cut off the engine and release the flight stabilizers and allow the lift, drag, and weight of the glider to determine its trajectory. I was so pleased that the mathematical model so accurately described the motion of the glider. The model predicted a max height of 3870 meters in the initial loop, and the data, the result in the game, is very close to this. You can see the model predicts the glider returns to about 2,500 meters. And it does. And look how close the data, the results in the game, match the mathematical model predicting the second peak in altitude at about 3,290 meters. And now one more example in Microsoft Flight Simulator. Here we get 2 loops. Collecting data from the game, I find a max height at 9,820 feet. And with the lift and drag constants that I used here, the mathematical model predicts a max height close to this at 9,662 feet. In the data, the glider drops to a height of 8,600 feet at the low point or trough, and the model puts this altitude very close at 8,630 feet. And we can see our second peak in the data at 9,774 feet, and this matches closely with the mathematical model too. We've seen a simple mathematical model that matches closely to a more complex mathematical model running in the game, which models a real-life phenomena in gliding motion. I'll close with a phrase that I've had a lot of fun thinking about as I've worked on this project, and that is, games are mathematical models. Okay, that's it. I'll end here. Thank you very much for watching. I hope you found this to be fun and educational.